This is problem 1395, it's on page 727. A mixture of ideal gases has a specific heat ratio of K equal 1.35 and an apparent molecular weight of M equal 32 kilograms per kilomole. Determine the work in kilojoules per kilogram required to compress this mixture isentropically in a closed system from 100 kilopascals and 20 degrees Celsius to 1000 kilopascals. Well, let's draw what's going on here. This is a piston cylinder device. So we know that the gas mixture is compressed. So let's draw a little bit of space here at the beginning. And for state 1, we'll write that the temperature in that state is 20 degrees Celsius. And since we're dealing with mixtures and properties, we might need this in Kelvin, I don't know. Let's just jot it down. 293 Kelvin. And the initial pressure is 100 kPa, kilopascals. Now what's going to happen, isentropically, is that this is going to be compressed. This gas mixture is going to be compressed to state 2, such that the pressure in state 2 goes up to 1000 kilopascals. Now we can't say much about the temperature. I think the temperature is probably going to change, but we know this is true. Now some properties of the gas, the heat capacity ratio is given as 1.35, and the apparent molecular or molar mass is 32 kilograms per kilomole. And all we're trying to find is the specific work in kilojoules per kilogram. We don't care how big the system is or the extent of the system, how much mass is in it. We just want to know how much work it takes to compress each unit mass in that system to these conditions. So I think what I'm going to do is realize, well, this is just boundary work flowing in, isn't it? So I need an expression for boundary work in this case. Now, if you look at the expressions that we have for boundary work, if you go back to, I believe it's either chapter 3 or 4, let's see. Here's chapter 4, yeah, it looks like chapter 4. It is chapter 4, page 195. If you look, I had you write in a couple of extra equations, well, maybe one extra equation. The one extra equation I would have had you add is the one for isentropic processes. And in that case, it looks a lot like a polytropic equation, except, so this all looks like a polytropic equation, except for the fact that it's 1 minus k rather than 1 minus n, where k is the specific heat ratio. Now, since PV equals RT, I recognize that I could probably replace this with RT. So basically RT2 less T1, and I've basically just transferred my ignorance to one number. I know T1, I just don't know T2. If I knew T2, well, I'd be pretty much done with the problem. Since it's compressed isentropically, I can relate the temperatures in the two states, T2 over T1, to the pressure ratio. In fact, the equation goes like this. T2 over T1 equals P2 over P1, where P2 over P1 is raised to the power of K minus 1 over K. And so rearranging just a little, T2 equals T1, P2 over P1 to the K minus 1 over K. And so all I got to do now is plug in the numbers. It's a good thing I changed that temperature because now I need the absolute temperature, 293 Kelvin. The pressure ratio, 1,000 over 100, is just a 10 to 1. So 1,000 over 100, this is just 10 to the 0.35 over 1.35. I just went ahead and subtracted the 1 from K as I wrote it. And that comes out to a temperature in state 2 of about 532.3 Kelvin. So there's the temperature in state 2. The only other thing I need is the gas constant R, but that would be equal to the universal gas constant divided by the molar mass of the mixture. The molar mass of the mixture, that's funny, it's three M's. Oh well. So 8.314 kilojoules per kilomole per Kelvin would be the universal gas constant. The molar mass of the mixture they gave us was 32, not point anything, kilograms per kilomole. And so the universal, or the gas constant itself, comes out to about 0.2598 kilojoules per kilogram per Kelvin. So I can just plug everything in now. Let's see, the gas constant, 0.2598 kilojoules per kilogram per Kelvin. The temperature in state 2, 532.3. Temperature in state 1, 293. Both of those are Kelvin. Divided by 1 minus K. Now this K is the ratio of heat capacity, is the 1.35. And unfortunately I'm out of space here, I think, so let me just erase this bit. And so plugging all that into your calculator, the Kelvin's the only thing cancels. We'll get the boundary work, the specific boundary work required out of this. So when you plug it all in, you get negative 177.6 kilojoules per kilogram. Now, this negative sign might concern you, but all that really means is work flows into the system. Remember the boundary work equation, which is that boundary work equals the integral of P dV. This boundary work equation has a sign associated with it, an SIGN, and that is that work out is positive and work into a system is negative. That's why in the past we've used a sign convention assuming that work out is positive. It's because then you kind of just expect that when you get to the boundary work equation. Turns out it's the same thing with the steady flow work equation for devices that have fluid flowing through them steadily and are either doing work on the fluid is providing work. In those cases, those equations will give you a positive sign for work flowing out of the device and a negative sign for work flowing in. In our case, of course, we were dealing with a closed system, so it was just boundary work as our primary concern.